my presentation on broad learning, not deep learning. I'm Ingo Elsen. I recently started at the Aachen University of Applied Sciences. Before that, I was working at T-Systems, a subsidiary of Deutsche Telekom, and the branch I was working for does a lot of stuff for railways, for airports, so the airport systems in Frankfurt, Berlin, Beijing, Manila are built from that group, and also the toll collect systems for trucks in Europe are built there. And that's the reason why Deutsche Bahn contacted us to build a system that can improve the prediction of train arrivals. And I will show you how we have built the solution. But first of all, I want to give a motivation why we shouldn't do everything with the high deep learning. And we've heard in the keynote lecture that there is no one-size-fits-all solution. And here are some examples of real-world problems that are not always made for deep learning. What does deep learning require anyway in order to be applicable to a problem? So first of all, we need a high number of data samples. And the first one is the well-known ImageNet, and it has 14 million samples of true positives, true negatives, or here it is recognition of specifics of an image. And that is really one of the standard applications, we all know. The other four come from my business area. One is the recognition of sports images, so it's really far less samples. Then it's industrial images, where boxes had to be monitored in a chemical bath, so it's really much more difficult to acquire these images. So also some orders of magnitude fewer samples. And then in industrial measurement, and that's even less. The only thing that is exceeding in the number of samples, that is what I'm talking about today. That is the train positions where we have more than 1.5 billion. As a matter of fact, today it's more than 3 billion separate samples that can be processed. But the second requirement is that you must have some way of automatic control of the data quality, or on the other hand, you need to have lots of people and money. So for ImageNet, the acquisition process was doing hand labeling of the images. So in order to do that for 14 million, that's quite a cumbersome and costly process. This was a community effort, by the way, so no money was involved. But then if you have commercial applications, like we see here, this hand labeling is really costly. You cannot do that for billions of data sets. So you need some automatic process, and this is what we did for the industrial images. And then in industrial measurement, the problem is that even today, and everybody is talking about digitization, Industry 4.0, there is lots of manual acquisition. And manual acquisition means it's an error-prone process, and that means the data quality is not good. And the last point or the last requirement for deep learning to be applicable to a problem is you must have high-dimensional data. This is the case in the ImageNet. And it was the case for industrial images where we had high resolution. But here, this is an application from sports for football. There are two leading companies in goal control technology for football, and they try to detect the ball in the image, whether it's behind or in front of the goal line. And these images are taken with high-speed cameras that are extremely fast, more than 400 frames per second, but they have lower resolution. So the images here are only 16.16 pixels large. And then all deep learning algorithms collapse after a few stages. And then in the last case here, the last two cases for industrial measurement, the dimensionality is even much lower. So 14 types of sensor measurements in that case, And even for the training positions, it's less than 30 dimensions. So deep learning or convolutional neural networks as a speciality of that are not applicable here. So we need to have something different. And this something different is the broad learning approach, where we go there and say, okay, if we have a problem that can be decomposed into multiple sub-problems, then I can still apply machine learning. There are some things that need to be considered there. So the solution of the overall problem can be seen as a combination of solutions of multiple smaller problems, where each sub-problem can be solved with few or no dependencies, local dependencies from the other problems. So basically these are graph-related problems that we are going to see in the next few slides. And the last requirement is, for each sub-problem, you need to have enough data. So if we go to that table, it would not be sufficient that you have a high amount of data in total. So you must have enough data for every sub-problem of this application domain. The benefits then are that smaller problems can be solved with superlinear scaling. The reason is that most of the machine learning algorithms have quadratic or at least n log n complexity. So if you can boil down the problem into many sub-problems that then are combined together, your computational requirements are shrinking faster than the sub-problems are shrinking. And this is much easier to parallelize. So if there is no or only few local relationships of the sub-problems, you can easily put that onto a cluster and do parallel computations on that. Compared to deep learning algorithms, let's imagine a huge convolutional neural network. If you want to distribute that over a huge cluster, that's really difficult then to collect the single results on each cluster node to form together the final result of the neural network. And local errors, so if one of the sub-problems is really difficult to solve, you can isolate that and limit the effect of the sub-problem to the total solution. And the last benefit is, still, again, this is the non-size-fits-all approach. There are sub-problems that might not be solvable with a standard approach. And then you can apply different solutions to specific sub-problems in the application domain. And that was the task we were faced with. It's the prediction of the arrival of trains. This is a screenshot of a demo which we did when we weren't allowed to announce the customer. So we had some fantasy route all over Europe. As a matter of fact, it's an ICE running from Kiel to Munich, and it's the real data we were using, which could easily be seen from Barcelona to Marseille, which is a few hundred kilometers, and it's underseas, and it only takes 5 minutes on schedule. This would be the realization of the Hyperloop. Yes, you have a question?
Really quick question. What was the use case, what was the business benefits of using AI as opposed to just real-time data?
Once again, please.
Hi, my name is Wayne Rowe from RAM Science. What was the business benefits of using AI for this business requirement as opposed to just actually using real-time data?
Yeah, so the basic benefit that Deutsche Bahn wanted to see is that they want to improve, and this is one of the 5 V's of big data, which are often put on this type of problems. They wanted to improve the passenger information for running and scheduled trains. So the solution they have today is not accurate enough. And they said, okay, we have been collecting data over a large time span. So I think they have 5 years of data, of which we were using 3 years. And this is the already named 12 billion data sets So these data sets are train positions. We see that on the next slides. And then they said, we also have a real-time requirement, so velocity, we have a real-time requirement for operations. We want to know as soon as a train sends its position, we have in total 10 seconds until which we want to know the final schedule for the rest of the route. And that is a real-time requirement, and as a matter of fact, the system consists of, I think, about 62 different IT systems, of which we are only one in the overall process. So these 10 seconds in total boil down to less than a second for our system to do the prediction of the complete train route. And then for each of the messages that came in, we needed to check the data validity. So we see that on another slide where I have some samples for that. And we must merge multiple sources. This is the variety of data. So we get the messages of the trains, we get messages from the railroad network, from the tracks, and we also get the schedules. And in the future there will be even more information which comes in. And the value is that the passenger information should be improved. And as a matter of fact, Deutsche Bahn said, we are only giving away a contract if you achieve a certain level of improvement. If you don't achieve that level of improvement, all your efforts are for free. We are not giving away a contract. So the basic problem, and that makes this problem very good decomposable, is that the railroad network can be considered a graph with around 33,000 vertices, of which 22,000 are used by public transport trains. And one vertex in the network can be a stop on a tour for one train or a run through for another train. Consider high-speed trains, they are not stopping at every railroad station, and local suburban trains are stopping much more often, but they are used, most of the edges in the network are used by multiple types of trains. So there are only few edges in the graph. For instance here, this is the high-speed track between Cologne and Frankfurt, which is only used by one type of train. And then another thing which we were facing was that we don't have data for all existing types of trains. So the railroad network is not only used by public transport, but also by freight trains, for which we're not getting data, but their movement is influencing the overall state of the network. So our assumption was that we will see the effects in the other data of the public trains, and because we have so many data sets, we should be able to cope with the missing data. And the last thing is, and that is the veracity of the data, we cannot expect data to be correct all the times. And that was something we were facing, and these are the real-time messages of trains. A train is sending its position, so I'm here. There is a coded station ID, there is a timestamp, there is the expected time, there is the current time, there's the track where the train should be running, the track where the train is running, and so forth. And the most common error in the data is that the time is not accurate. We did receive messages from the future, and we did receive positions of Berlin suburban trains sending messages from Denmark. And these are things that happen not too often, but if you have these type of errors in the data, they are messing up your predictions. That's really a tricky problem to cope with, because it's easy to see if I know it's a suburban train, it should be in Berlin, and then if the position is crappy, that's easy to sort out. But if you have, like say, people setting the clock in the train, and they are only off by a minute or so, just by typing in erroneously the current time in the train, then it's difficult to cope with that problem. So the human factor is still involved in the data. The schedule data is most of the time correct, but that was something we were only seeing lately in the process. When we got the data, we've seen that there are two different types of coding, and that was depending from where we got the schedule. And that is also something you need to sort out in the process of cleaning up the data. And then if everything was cleaned up, then we could get into doing the predictions, and here is what the standard approach is that you can see from literature. So we have been collecting all the messages, and all the messages we can put on a vertex. Then we get probability density distribution on the vertex about the time that is needed to travel along the vertex. The same holds true for a station where we are in, and then you have the time in the station, and you get a probability density distribution for that as well. What you can do then is you simply add up the expectation value of the distributions, which is a nice way to do that because you can pre-compute everything here, and then you are really fast. Unfortunately, you are also not very accurate. So this approach, we could quickly show that that is not leading to good predictions. The next one is the mathematically more accurate is you do convolutions of the probability density functions. And that is the approach you can find in the literature as the current state of art in railway operations. And we will see on the next slide that this has problems as well. And the last thing, this is what we are doing now for most of the vertices, is we are summing up the local predictions of neural networks. And in order to see what we can do with the data, we said, okay, let's look here at the state of the art, how good can we be here? And then we said, okay, we do vertex-specific histograms in order to get probability density distributions. And then we said, okay, let's make some feature categories. For instance, the type of vessel. Is it a suburban train, regional train, long-distance train, high-speed train? Which time of the day is the train traveling? What is the current train delay, and so on? And we created from that 144 different histograms for the vertices. We were cooperating with a chair for train operations of the University of Dresden, and these guys said, okay, you have to model everything Erlang K distributed. And then we analyzed the data, and that's the nice thing if you have a huge cluster and all these data sets, and from that you can easily see none of these distributions will be proper fit into an Erlang K model. So what you can see from the data here, and that was something we found out also in the discussion with the customer, is that there is a human factor involved. The guys sitting on the locomotive, they always try to be on time. And that is why we always see a peak in 0. If the train, and most of the trains are on time, so what they are trying to do is, if they are ahead of time, they are slowing down. If they are not in time, they are speeding up as much as they are allowed to, and then you see a peak around 0. And the other thing that we have seen is that for many situations we are not getting too much data. And you need to cope with that as well. So to build this kind of cluster is quite difficult. And that makes the standard approach, or the classical approaches, very difficult to apply to that. Today's solution that is implemented in the existing system is a linear approach. So if you are 5 minutes late now, you are 5 minutes late the rest of the tour. That is spiced with known events, but you cannot expect to be always to have always accurate data, because there's lots of manual intervention that you don't see. So one thing that happened to me, I was traveling to Cologne, trying to catch an ICE to southern Germany. And then I was asking the guy on the train, are we going to make the 511 in Cologne? And he said, which one, the 511? Yeah, no problem. The guy on the train is my brother-in-law. I give him a call and you're going to catch it. And that is something you are not going to see in the schedule here. But sometimes you see that in the data. Because the messages will be captured anyway. And this solution is completely agnostic with respect to already known information. For instance, which type of vessel am I, or which time of day is it? Am I in a high traffic time of the day? But that is not considered here. The other approach, the collusion of PDFs, is also problematic because some of the PDFs are not very smooth. We've seen that in the pictures before, and you cannot do a complete histogram on the vertex. You need to separate that at least for the type of vessel. And then, even for smaller tours, the PDFs are very wide. So if you have a tour of 20 train positions, then your overall probability for each of the potential delays becomes very low. For a long distance, then to generate an expectation value here is basically just guessing. So this approach is not very well suited for this type of problem. What we then did next was, let's see if we can cluster the data in a way that we can say, okay, let's improve these feature sets. And then we used two algorithms, one's a self-organizing map, a type of neural networks, and a k-means clustering algorithm to see if the delays can be clustered properly. But then we have been quickly seeing that we found out clusters, but within the clusters or over the clusters as a total, the delays were more or less evenly distributed. So that was no good feature as well. So then we said, okay, let's use some supervised learning approach, still decomposing the problem into many, many small subproblems. Because for each vertex, we have been finding good data. So the next approach was using support vector machines, a supervised learning model. I'm not going into details here, but the support vector machine tries to approach the distribution based on the data. And we did it in a way that we used as input features all the features we had before, used for the clustering or for the generation of these 144 histograms, but then in that case we didn't do a separation. We just said type of vessel is one parameter, the current delay in seconds and not in 3 groups is another parameter, the type of day, the time of day, the expected travel time, and some other non-disclosed features as well. And then for each vertex of a train tour, we were training one neural network. And the nice feature about that is we have the data here, but there's no connection to the data here that we need to consider during the training. So we can train everything in parallel. And that means we have a vertex-specific training, so one neural network per vertex. And this is extremely well parallelizable on an existing cluster. And then we had a huge cluster with 30 nodes. We could train the 22,000 neural networks in 33 minutes. Quite fast. Why is this so important? Because over the course of the day, we are getting new messages. 1.5 million messages a day. And then, if you can train that fast, you can retrain your neural networks every night, employing the data that you captured over the day. And that is important because, for instance, special situations come and go, like a construction on a railroad is, today we have this construction and 2 weeks later this situation is gone. And that's difficult to map into a regular schedule, but it's easy to see from the data. And with that approach, it's also easy to employ into your prediction automator. But then still there are some situations where this neural network approach is not optimal, and what we are doing is every night we are also have a competition of some dozen algorithms competing against each other for specific situations, and then we are looking into the current situation of the train, and then based on that situation and its position, we are choosing the algorithm that is going to deliver the best prediction here. Then we are connecting all these informations together and get a final prediction for the total train arc. Then, as another approach, we are also doing something with the data that is weighting the historical data. So one thing that is very important is the last season, in terms of 1 year back in time, is more important than 6 months back in time, because we have similar conditions 1 year ago. Public holidays are more or less in the same time span. We have more or less similar weather conditions, and we have more or less similar traffic conditions with the people going on the train and off the train. And then also we are modulating it in a way that the farther away we are in time, the less important is the data. With that approach, we could also show that more than 3 years of data are not, do not deliver more benefit. So we tried with 4 and 5 years of data equally weighted, and the performance was less than we could achieve with that weighted approach. That in total had to run on an architecture, and for that we are using a standard Hadoop cluster. The only difference from standard nodes is that we are using lots of RAM in the cluster. The reason is that for real-time predictions, we're loading all the neural networks into RAM, and that makes the cluster running pretty fast. As soon as a message comes in, we can hash map into the main memory and find the right neural network to do the prediction. And with that approach, we could get down from 30 nodes to 4 nodes. The system itself can scale up to 50 racks with 50 nodes each. And that is one of the largest installations I've seen so far. But in our case, we are fine with 4 data nodes, 4 Kafka nodes, which is a messaging system to get the data in. And that is replicated in 2 locations to have high availability so that the service is running uninterrupted. The whole system itself is then made in a way that we have a Kafka connection to the customer system where the real-time data comes in and the real-time predictions go out, and some planning and master data that comes in via a separate channel, because here we don't have a real-time requirement. Schedules and master data are sent only once per day. And then these real-time messages go into the prediction jobs, and we see how this is implemented in the next slide. And there is a prediction control that is controlling how many jobs do I have. If a job stretches down, it gets restarted, and so on. And we are also collecting all the data in our system. We are continuously capturing the data that comes in over the day. So we have a complete database for the training run in the night. And the machine itself, on in the total, in the cluster as a total, there is on the node, there's a node processing, And every free node, it's a classical farmer-worker pattern, is capturing the next message, does a prediction, and sends it out to the customer. Why does this work? Because any message coming in is independent from other messages. That makes the problem also decomposable in time and very efficient to compute. And on the local nodes, we're using Apache Storm to do that. We have a local thread pool running, so we can use all the computational power in this multi-core configuration on the Hadoop cluster. And there again, we have a message queue where the prediction is done, rolled out, and then it goes back to Kafka. And we have some preloading where all the neural networks are loaded from a database into the RAM of the node, so that it is, each node can compute any message that is coming in. So it's a very flexible system. As soon as we see that we don't have enough computational power in that system, we just add more nodes. This is very cheap to handle during operations, and all the nodes are more or less identical. So if one node crashes down, it's easy to replace. If we need more nodes, it's easy to add to the system. So we have a very cost-efficient solution when it comes to operation of the total system. The overall result is now that on 1 billion data sets, we are training 22,000 neural networks every night in a 90-minute time span. So we have lots of leeway to add more features to that. We have a real-time requirement for operation, sub-second latency. The current system needs less than 600 microseconds to predict the waypoint. The longest tour, and I took the train with the longest tour from Lübeck to Munich, takes less than 35 milliseconds to predict in the system. There is still some bookkeeping to get in and out of the system, but 35 milliseconds is quite a figure to be in a real-time mode where you have 10 seconds in the total system to do the prediction. Any incoming message that we are seeing is checked for validity, and we are also continuously checking the quality of the predictions. And we are merging multiple sources, not only the trains and schedules, we also added network operation systems, and in the future we will add even more sources, which we see on the next slides. And the current system, and unfortunately it's under NDA to produce concrete figures, it is at least 2 times better than the existing solution. So what we are going to do in the future is we will store, and we are already storing all incoming messages, and we want to keep the performance of the system even when we are integrating new sources and algorithms. So the next step will be to add information from public transport and passenger counting systems. So if you know how many people are coming in, and this is something that is special, for instance, for large cities, if you have football matches or so, and it's a difference on Saturdays whether the team is playing in its hometown or it's playing out of town, then these PAX counting systems can give additional benefits for the predictions, and we will add the predictions from local intermodal traffic on control systems. That's it so far. Thank you. For those that are interested, I'm open for questions now, and I have a demo running on my laptop, which we can look for those that are interested at outside of the room or in the time that is left now. Thank you very much.